Welcome to chapter 6, where we will see an overview of organic reactions. Basically, we will see kinds of organic reactions, how organic reactions occurs, the mechanisms of organic reactions, radical reactions, polar reactions. An example of a polar reaction: addition of HBr in ethylene, using curved arrows in polar reactions mechanisms, describing a reaction, equilibria, rates, and energy changes, describing a reaction, energy diagrams, and transition states, describing a reaction, intermediates, and then we will do a comparison between biological reactions and laboratory reactions, a deeper look, where the graphs come from, Okay, for this chapter it's necessary to know not just what occurs, but also why and how chemical reactions take place. Okay, basically we have several kinds of organic reactions. One is the addition reaction. For example, we start with ethylene, here you can see, and we add HBr. What is happening is that we generate bromoethane. We have the addition of HBr over the double bond. Elimination reactions, that will be more or less the opposite. For example, we can start with ethanol and then we add acid. Basically, we eliminate one hydrogen and the OH to form water and generate the ethene. Basically, we are eliminating water from the starting material. Substitution reactions, we have, for example, this ester, and we add this alcohol. This alcohol attacks the ester, and what we generate, water. This water attacks the ester, and what we generate is the carboxylic acid. And as a byproduct, we get methanol. Mainly, we substitute a OH for a methoxide for a OH. And finally, we have rearrangement reactions that basically are movements of protons or atoms in the same molecule. For example, we have this dihydroxyacetone phosphate, and basically what we can do is to reduce this ketone, oxidize at the same time this alcohol, and we generate the glyceraldehyde free phosphate. The only that we make is to change this proton to here from here. Okay. Basically, we have these four types of reactions, and now we will describe how a reaction occurs. Which bonds are broken, which bonds are formed, the relative rates at these steps. And when we break a bond, we have two possibilities always. One is that we break the bond symmetrically. That means that each atom takes one electron of the bond, and we form both radicals. Or the other way to break the bond is simply that one atom, normally the most electronegative, take both electrons, and we have one anion and one cation. If we have a symmetry breaking of the bond, that means we form radicals, we have a radical reaction. If the breaking of electrons is not symmetrical, that means we have an anion and a cation, we have polar reactions. And the same, to form reactions, we can start with two radicals, they join the radical, they form a bond, and this will be a radical reaction, a forming radical reaction. And if the opposite, if we have an ion attacks a cation, remember always the movement of the arrow is from the electrons to the positive charge, never the opposite. Okay, positive charge means lack of electrons, we don't have anything there. That means that what has to move is the electrons. Okay, we can have this attack to form the final bond. This is an example of a polar reaction. If we focus on radical reactions, the radical reactions contain an atom with an odd number of electrons, usually 7 because it has to be the octet, in its valence shell. That means here you have an example, okay, A and B. this has an unpaired electron, it's breaking this bond, and we form another radical. Okay, or we can form basically a radical attacks one double bond and we generate another radical in the other carbon. Or basically, when we attack this with light, we form a radical here, and then we transfer one chloride to one of the hydrogens. Okay, that means we always have in the radical reaction three kinds of steps: initiation, propagation, and termination. And this is very important. Initiation, for example, we start with the chloride. We have a chloride, we irradiate the chloride with light, and what we have is a breaking of the chloride-chloride bond. In this case, the breaking of this chloride-chloride bond is symmetrical. That means that we generate two chlororadicals, as you can see here. Propagation, this chlororadical is reacting with methane. The chloro is reacting with the hydrogen, forming a bond, and at the same time we're breaking this bond between the carbon and the hydrogen in a radical way. Okay, remember that the hydrogen cannot expand the octet, cannot expand, they only have one orbital. That means that if we form a bond, we have to break a bond. And what we form is hydrochloric acid plus the radical methane, CH3 radical, methyl radical. Okay, then this methyl radical is reacting with one molecule of chloride, generating the chloromethane plus regenerating, forming again a molecule of chloride radical. That means in this propagation we generate the same that we add. We add a chloride radical, we have to generate a chloride radical. This is a chain reaction. Finally, the termination. The termination is when we extinguish the radicals. And this could happen for several ways. Here you can see that two chloride radicals react together to form chlorine again. One chloride radical and one methyl radical is reacting to form chloromethane, or two methyl radicals are reacting together to form ethane. In all the examples, as you can see, in the termination step we kill the radical. There are no more radicals to work with. Okay, in the initiation we create a radical. In the propagation we use a radical and we generate another radical. In the termination it's over. No radicals anymore. What about the polar reactions? Okay, the polar reactions are based in the polarity. Okay, normally we have an atom that is more electronegative than the other atom. For example, we have here a carbon chloride bond. Obviously the chloride is more electronegative. That means that we'll have a density negative charge over the chloride, while the carbon will have a density positive charge. Just the opposite than methyl lithium. In methyl lithium, the lithium will have a positive charge because it's more electropositive than not the carbon, and the carbon will have a density negative charge. We can increase the polarity of these bonds by, for example, if we have an alcohol, by protonating the alcohol. Now we have water here. This is charged positively. That means that it's attracting more electrons from the carbon. The carbon becomes more positive and the oxygen becomes more electronegative. Okay? Here you have the polarizability of different functional groups. Okay? You can see here in all these groups there one carbon that is density negative and one